Okay, so let's look at our notes. We are on chapter 8, 8.1, where we talked about hypothesis testing in the first lesson of 8.1. So the null is the H naught, and that is the one that is equal. So this is pretty important to look back at as you're doing your hypothesis testing. So for all of chapter 8, this is a really helpful guide on what to do. So identify the claim, write it as symbolic form, write it in symbolic form, and then write your hypotheses. So H naught is whenever whatever you're looking at is equal. So you say like P equals 98.6. And then the claim is the HA, H alternative, or H1. That is what you're testing out, whether it's P is less than 0.2 or whatever that is. You look at your significance level, and then you are going to find your test statistic and then make a decision. So part 7 is when you make a decision. For the p-value method, you are going to compare the p-value with your significance level. Alpha is your significance level. So whenever I make my decision, I write p-value is what to alpha, or to the significance. And then I can plug in my either less than, equal to, or greater than. And then I can either reject the hypothesis, the null hypothesis, or fail to reject my null hypothesis. And then the critical region method is whenever you draw your normal distribution, and then let's say it's a right tail, this would be called your critical area, critical region. So if the test statistic is in the critical, you reject your null hypothesis. And then if it's not in that critical region, then you fail to reject. So we're, again, looking at the hypothesis and deciding whether that claim is true or not. So let's look back at our drone example. So we wrote this yesterday, all of the numbers that we need. So we needed N is 1,009, P is 0.5, Q is 0.5. So the way you get P and Q is from the claim. So the claim says majority of people, so that's half or more. So no's is considered your success, and yeses is considered your failure. So 0.5. Your sample proportion, that's found by doing how many they found were not comfortable over your total. So you could also put sample proportion P naught or P hat as how many X successes over total, or your sample size. So that's your P hat. Significance level. We are going to use, since it didn't say, we're just going to use our 0.5. So that's like 95% confidence. 0.5, 0.05. There we go. Our test statistic is going to be found by using Z. So this is P hat minus P over square root of P times Q over N. We're going to be using this a lot. We used it in chapter 6, and then we used it in chapter 7, so now we're using it again in chapter 8. So let's plug in. So step 6 is actually finding what that z-score is. So P hat was the 0.54. And what I found as I was doing some examples is that you need the actual. If you're doing this by hand, they don't like rounding even to 2 decimal places.
Please pardon this interruption, but seniors, this is just a final reminder that the deadline to...
So our p hat was, let's see, how many did they say? 545? Yeah, 545 over 1,009. So 545 over 1,009 minus the p, which is 0.5, over square root of p times q over n. Lots of fractions in this. Yeah. So that comes out to 2.5. If we were to round, 2.55. So whenever I did it originally, which it doesn't make a big difference except on one problem I did today. It made a big difference. And that was in, I don't know what section it was. I think it was 8.2. So it's not that far off, but it just seems like it gives you a more accurate answer if you just use the x over the total successes. Okay, so that's 2.55 is our z. So remember, when we want to use our z, we're going to use our table, A2. That's the positive z-scores. And we want to go to 2.55. 2.55. 0.9946. So it was 0.9946. And so that's the area to the left. So we do this, and we have a z of 2.55. But we want to find, because it says the majority, so that means greater than. So we're finding that probability. So it's the area to the right. So what we just found was area to the left, 0.9946. So to find the area to the right, which is our p-value is the area or probability, we're going to take 1 minus 0.9946. .0054 was our value whenever you subtract it. So then we're going to, when we look back at this, we're going to make a decision on step 7. We're going to compare the p-value to our significance level. So the p-value is 0.0054 is something to our significance level, 0.05. This is smaller. So this is less than. So it's a smaller area. So whenever it's less than, then it says reject our null. So reject H naught, which that was that the P was equal to half. So I want to show you something I looked up whenever I was, trying to come up with a claim and what this actually means. So what this means, and I went ahead and put this on the notes on the Google Slides, but I'm going to print this out for y'all in class. It says the null hypothesis, if we reject the null, that means there's sufficient evidence. The evidence is sufficient to reject the claim. That's about the null. But about the alternative, which the alternative is what we're actually looking at. Do majority of people feel uncomfortable about the information about drone deliveries? So if we reject the null, it says there is sufficient evidence to support the claim. So that's what we are going to write. There is, and I'll switch it over to mine in a second. Sufficient evidence to support the claim. And what was the claim? That majority of people are uncomfortable with drone deliveries. So I'm not going to write that out, but that's what it means. You just refer back to the claim. Okay, so the critical region, which is rejection region, is the area corresponding to all values of the test statistic that cause us to reject the null. So a two-tailed is whenever we're looking at our alternative being like x does not equal 0.5 or something like that. That's just an example. So the two-tailed, you have the not equal. This is for your alternative. Our null is always equal. So don't forget that. The null is always equal to whatever it is, say 0.5. But our alternative, that's what our claim is testing. So left-tailed test is whenever you use the less than symbol. So let's write that as p is less than, I'm just going to make up like 0.2. So everything below that. And then a right-tailed alternative would be if p was greater than, let's say 0.3. So this is where you look at the critical region. Where does it fall? The p-value method, that's the one that we used on the drone example. In a hypothesis test, a p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming the null hypothesis is true. So be careful on this. We have all these things that have a p in them. So our p-value is going to be our probability, which is also dealing with the area. We find our p-value using table A2 or the technology. It's the 1 prop z test. The P is our population proportion. And it's our claim. It goes along with whatever the claim is from our H alternative. And P hat is our sample proportion. Which is found by doing X over N. X is how many are considered successes. And N is your sample size or trials. Confidence interval was from chapter 7. A confidence interval is the estimate of a population parameter. It contains the likely values of a parameter. We should therefore reject a claim that the population parameter has a value that is not included in the confidence interval. So our confidence interval, we could look at the two values. If it doesn't fall between those two values, then we will reject the claim. So between two values. If it's not between these two values, let's say it's over here, then that means we're going to reject our claim. If it's not between A and B. If it's outside of that area. Make a decision about whether to reject or fail to reject the null. So those are the two decisions. We can either reject the null or fail to reject the null. We can't accept anything. We just have to either reject or fail to reject. So if it's a less than or equal to, we reject the null. If P is low, null must go. It's a way to remember it. If P is high, the null will fly. So it flies through, it's good. We're going to fail to reject it. If we fail to reject, that means null is okay. Let's see. Wording the final conclusion. So refer to this table to help you write your response. So original claim does not include equality, and you reject the null. There is sufficient evidence to support the claim. Or if you fail to reject, anytime you fail to reject, it's not sufficient evidence to support the claim. If you reject, there is sufficient evidence to support the claim. If the original claim includes equality, so like if our HA is, let's say, X, or I guess I should say P equals 0.05 or doesn't equal 0.05, and you're rejecting your null, there is sufficient evidence to warrant the rejection of the claim. You fail to reject the null, there is sufficient. So the wording is kind of confusing. So that thing that I showed y'all a minute ago, it'll be on the notes. That is definitely helpful for you to decide how do you respond. What is the actual conclusion? Okay, so we never say accept the null. Accept is misleading and implies that the null hypothesis has been proven. But you can never prove a null hypothesis. You can never say that it is true the population will always be equal to 0.5. You can't do it. Because remember, the null hypothesis is always that it equals something. We can't prove that it's going to always equal half. But you can fail to reject, which says that the available evidence isn't strong enough to warrant a rejection of the null. So some conclusions have a lot of negative terms, which can be really confusing. So instead of saying this, it says there is not sufficient evidence to warrant rejection of the claim of no difference between this and that. So instead you would say, until stronger evidence is obtained, continue to assume that the population proportion is equal to 0.5. With hypothesis testing, you can have different types of errors. So a type 1 error is the mistake of rejecting the null when it actually is true. The symbol alpha is used to represent the probability of a type 1 error. So this is rejecting the null when it actually is true. So an example of this would be rejecting a perfectly good parachute and refusing to jump. You're saying no because I don't think it's going to work. I'm not going to jump. But it was good. The parachute was good. You could have jumped. And then the type 2, so that's a type 1 error. So then the type 2 error, the mistake of failing to reject the null when it actually is false. So you want to reject the null because it's false. But if you have an error, you're not rejecting it. You're basically saying it's true. So this would be failing to reject a perfectly good parachute and jumping out of the plane. So to help you with the 2 errors, this is kind of a chart. So if the nature of the true hypothesis is true and you fail to reject, then that's a correct decision. If you reject it and the nature of the null is false, then that's a good decision. But if you reject it but it's true, that's a type 1 error. If you fail to reject but it's false, then it's a type 2 error. Okay, so you can look back at this, but let's go ahead and go to the example. Consider the claim that a medical procedure designed to increase the likelihood of a baby girl is effective. So the probability of a baby girl is greater than 0.5. Given the null and alternative, write the statements describing a type 1 and a type 2. So remember, our null is whenever it's equal to half. So they're saying the claim is that it's greater than half, so that goes in our alternate. So a type 1 error would be the mistake of rejecting the true null. So the following is a type 1 error. In reality, to get a baby girl is 0.5 to have a baby girl. But sample evidence leads us to conclude that our probability is greater than 0.5. So in this case, you would conclude that the medical procedure is effective when it really has no effect. The type 2 is when you conclude that the medical procedure has no effect when it is really effective in increasing the likelihood. We have already done the writing the hypotheses, so let's look at number 3. It says the claim. The mean pulse rate in beats per minute of adult males is equal to 69 beats per minute for a random sample of 181 adult males. The mean pulse rate is 70.6 beats per minute, standard deviation of 12.3 beats per minute. Find the value of the test statistic. So we are dealing with the mean. We're not dealing with proportion. So when we deal with the mean, we're going to use T. Let's go ahead and write what we know, though. We know that the mean pulse rate of all males, so mu, is 69. In a random sample of 181, so n equals 81, the sample mean x bar is 70.6. So it's higher, just by a little bit, with a standard deviation of 12.3. Find the value of the test statistic. So we need to find our test statistic. So this is not Z, because Z is the proportion. So this is dealing with the mean. So we'll look back at 7.2, I believe, where we do T. Our formula for a test statistic when we're looking at means is x bar minus mu over S over square root of n. So plug in our numbers and go ahead and find T. Oh, this was sample. This should have been S. Sorry. Because it was a sample, not the population. So it's 1.75. So that's our test statistic. All right, let's go ahead and go through the next problem. Okay, so on this one, it gives us our test statistic of 1.25 is obtained when testing the claim that P is greater than 0.6. Use our significance level of 0.05. So let's write our null, H naught, and our alternative, HA. All right, what's our null? Yep, it equals the 0.6. So you look at the value of the claim and you say it equals for our null. Our claim is the alternative. So it's P is greater than 0.6. Okay, we want to identify if it's two-tailed, left-tailed, or right-tailed. So look back at our notes. Is it greater than or is it less than? Greater than, so we look at the greater than one. It's the right-tailed. So it's going to be like this. So we need to find our test statistic. So let's see, we need to look at, this is we already have our test statistic, 1.24. So we can actually put that right here, 1.24, and draw a line. And then since it's right-tailed, we're going to shade it to the right. And now we need to find the p-value. So we're going to use the table, A2. Because we're looking at area to the right, we need to find what's on left and subtract it from 1. So 1.24 0.8925. So 0.8925 is the area to the left. So it's right here. So to find the p-value, we're going to do 1 minus 0.8925. .1075. So that is this probability. That's our p-value. So we're going to write p-value equals 0.1075. And then we need to compare the p-value to our significance level. Our significance level is this. So p-value is something, significance level. So 0.1075 and 0.05. The p-value is greater. Whenever it's less than, null, what is it? The p-value is low, null must go. P-value is high, then the null will fly. So this, and you can always look back at the chart here. Since it's greater than, we're going to fail to reject. So fail to reject. And we want to write about the claim, which is our null. So I'm going to pull that statement, that little chart back up so we can look at about the alternative hypothesis. So fail to reject is right here. So it says there is insufficient evidence to support the claim. That P is greater than 0.6. I'll pull mine back up. So that is all for 8.1. 8.2 is more of this, so you'll start feeling more comfortable as we do more.